All right. If you're, it's concerning. Right. All right. Okay, great. Okay, so we're streaming. Okay, all right. So, great. And I assume you can hear it? Oh. Okay. All right. I think we're live now. Okay, great. So two things. So one, I've posted problem set 2. So the suggested due date is August 14th. I think there were problems there regarding the autograder, which I will fix hopefully next morning. But you can start working on the problems. And you'll notice that most of the problems are ones that we kind of worked in class on, so especially problem 1 and 2. So problem 3 is very similar to something we had done in class. Problem 4 is also kind of similar, but it's a more complex problem. So basically what we want to do is we want the median range for GDP per capita, right? So basically, you're taking in something that's like Gapminder. Then for every country, you compute the range of the GDP GDP per capita, and you want the country whose range is closest to the median of the ranges for each country. So what we mean by the range is how much did the GDP per capita change over the years. So for every country we have that, right? And then we have the median amount by which GDP per capita changed. And then we want the country whose range is as close as possible to the median. Right? So it sounds complicated, that's because it is, but if you just do it one step at a time, it's going to be fine. So you want to compute the range for each country. So that's similar to what we've done the other day with looking at ranges of temperatures. So once you have the data frame, and what you want to do is you want to actually output the intermediate result, see, okay, like now we have the range for each country. So then you also want to compute the median for the ranges. So that's fine. Now that's just a number. Once you have that, you say, okay, which country's range is as close as possible to the median? So that means that the range for that country minus the median, when is it as close as possible to 0? Right? That's the same as saying, is the GDP per capita range as close as possible to the median? Is the GDP per capita range minus the median as close as possible to 0? What does as close as possible to 0 mean? Well, just like the absolute value of the difference is minimal. Right? So if you do it one step at a time, it's very kind of a straightforward application of things that we've already done. But you have to do it one step at a time, because if you look at this problem just without really kind of without doing things one step at a time, it looks impossible. But it's not. Okay, all right, so that's that. So the autograder for this is gonna be set up. Wait, this is actually the wrong link. However, so I'll fix the link as well. Okay, so I think that's probably why people were saying on Piazza that it's wrong. It's the wrong link. I'll fix it, but the problems are very similar. I changed them a little bit. Sorry about that. So, okay, all right. So that's that. So basically with problems, yes, I think this is like the problem set for my old course or something, so I'll fix that. So basically we're done with having all the tools that you need in order to process data frames. Now, of course, a lot more practice needs to be done in order for people to become proficient at it. And we'll move on to something else. Yes? Yeah, it's gonna say, it's just that I posted the wrong handout with like slightly the wrong problems, so I'll fix the handout, and the autograder is already there.
Oh, did you fix it already?
No, the autograder is there, however, the handout is wrong. So I'll fix the handout, kind of just after lecture. It's basically the same problems, but like slightly different names, and also I changed up some of the problems. But yeah. All right, okay. So that's that. So what I want to talk about today is slightly different. And that's kind of the other piece of this mini course, which is predictive modeling. So trying to predict future data from past data. So here's an example. So this is referred to as linear regression. So let's say that you have this data set where for houses that were already sold, you have the size in feet squared, and you have the price at which the house was sold. Right, so Portland is even more expensive now. So that's kind of like this. So this was like $500,000 for 2,000 square foot. Actually, like by Toronto standards, extremely reasonable, but this is an old data set. So this is referred to as the training set. So a training set is a data set with past data, which you want to use in order to then be able to predict information about future data. So a bit of terminology here. So M would be the number of training examples. So this would be basically the number of rows in the training set. So the number of items about which you have the full data. So usually we'll denote the input variables as the x's. So input is the kind of thing that you would know about future data points to. So for example, here, the notion is you'd predict the price using the square footage of the house. So you'd know the square footage and you'd want to predict the price. So X would be the input. Sometimes people say features. Y would be the output. So the thing that you'd want to predict, you know it about the training set, but you want to predict about new data as well. Sometimes you'll hear target variable or something like that. So here's how the training set might look like, right? So here, every red X refers to a house that was sold. And for example, this house over here, so this little X was 1,500 square feet, and it sold for 250,000. Right? So that's this little X. So in general, you'll have lots of houses, so there's not necessarily kind of an exact relationship between the square footage and the house and the price, because you have like the neighborhood, you have kind of the quality of the house itself separately from the square footage, whatever, right? So how do you predict for new houses? Well, the idea would be like that. So you draw something like a line through the training data, so the green line through the red axis. And then you would say, well, my predictions are going to go along this line because this line is the best representation of the relationship between the square footage and the price. So for example, if I have a new house on the market and its square footage is X1, I would predict that the price for that house is going to be this much, so about 300. Right, so the 300 over here. And then if the square footage is like this, then the price that would be predicted would be I'll just go to the green line and I'll look up the y-axis here, so something a little bit under $500,000. Right? So algebraically it would be I would predict the price like this. So it would be like sum A0 plus A1 times size. The prediction would be just plug in the new x into this equation, where x is the size. And that's kind of the basic framework. So how do we decide how to draw this green line through the red crosses, through the red axis? Well, kind of you can just visually say, well, I want to draw kind of the line that's kind of approximating the red axis the best. But actually, if you think about it, there's multiple ways of doing it. So here's how it would look like algebraically. So you might say, okay, I want to find the best green line. So the green line's equation is going to be A0 plus A1x. And you might say, okay, like every time for every particular x, so for the ith row, for xi, I'm predicting this much. And then I know that the actual correct price was this much. And then I can say, well, the error was this much. Right? So just the absolute difference between the y and the prediction A0 plus A1x. Right? So again, what we're doing here is we're saying this kind of best green line has some kind of equation, so A0 plus A1 times size. And then we're saying if we predict for every x, so something people say retrodict for predicting a price that you already know, then we can say, okay, like for this red x, the actual price is under 250,000, but the prediction for this area would be along this green line, so that would be more like 300. So the error in the case of this particular x would be like 50K. Okay. And you might say, okay, so for every data point, we have this error. So the absolute difference between, in this case, the actual price and the price that you would have predicted if you just knew the square footage. And you could say, well, I want to make this as small as possible. That's a reasonable way of trying to draw a line through the data in such a way that the line is useful for predicting. Now, the problem, of course, is that you don't just have the one xi, yi pair. You have the entire data set, and there's no way to make... Of course, kind of you can draw the green line through any particular red x and predict perfectly for that red x, but you cannot do it for all of them. So there's trade-offs, right? So if you draw the green line through this x, you'll predict perfectly for this x, so the error is going to be 0, but that's going to be at the cost of having this one be really, really off, right? So the very first thing that people usually do, and we're not going to get into the theory of why that makes sense, but it turns out that under some mathematical assumptions it makes sense. What people usually try, at first at least, is to say, okay, the best A0 and A1 are going to be such that the sum of the squared errors is as small as possible for the entire training set. Okay? So for every y, we're taking the actual price, we're taking the retrodicted price, squaring that difference, and then we're saying we want to find A0 and A1 such that the sum of the squared errors is as small as possible. It doesn't have to be that way. So you could say, well, like maybe what I want to do is I want to find A0 and A1 such that the sum of just the absolute values of the errors is as small as possible. That would be a different criterion and would just lead to drawing a slightly different green line through the data. In some extreme cases, it can make quite a bit of a difference. Again, we're not like you take whatever ECE 286 and then you take some third-year courses where you have kind of the full theory of when it makes sense to do this or that kind of a priori. For a particular data set, you could just try different things and see what works best. So that's what's referred to as simple linear regression. So simple linear regression specifically refers to just having one input x, so for example, the square footage. And it's just saying, find me the green line, whose equation is a0 plus a1x, in such a way that for the training set, the sum of square differences between the actual price, the actual y, and their retradicted y is as small as possible. Graphically, this is roughly draw the best line through the scatter plot. So a scatter plot is just this. So kind of when you put all the points on the plot, that's called a scatter plot. So I want to do kind of very briefly something just kind of to show you that what I'm saying is not all kind of silly and obvious. Or, well, I guess it's like either silly or it's obvious. It's usually not both. So let's say that they have a scatter plot that's like this, right? And then I'm saying I want to draw a line through the scatter plot in such a way that the sum of squared errors is as small as possible. So what do I mean by the squared errors? Well, so for this point, the error is going to be this much, right? And that is because for this x, you would predict this y, and the actual value is this y. So that means that this, the length of this, the vertical line from here to here, is the error. Right? And similarly, for this guy, the error is going to be this much. Okay? And then we said for simple linear regression, what we're doing is we're trying to make it so that this squared plus this squared plus this squared plus this squared and so on is as small as possible. But that is obviously not the only way to do it. So for one thing, you could just say, well, like, why are we looking at the vertical distances? Might as well look at the horizontal distances. That would be different, right? You could say, well, I want to draw an ellipse around those points, and then I want to look at which way is the ellipse looking, and that would be my direction, and that would be a different thing. So this is neither looking at the vertical distances nor looking at the horizontal distances. It's actually just saying, just look at the data, like what's the orientation of the data, like at what angle does it lie? This is a different question from what minimizes the square vertical distances. Now, why might you like to do that? Or like how would you decide? So again, the full story is coming up in the future for you if you take the appropriate courses. But one thing you could say is, okay, the vertical distances, those are actually the errors, right? So if I look at the vertical distance, again, this would look like yi minus a0 plus a1xi. Well, this means something. So you could say, oh, it's the vertical distance, might as well do the horizontal. But no, the reason we came up with this in the first place is that this was the actual answer, and this was our prediction for the answer. And we're trying to make this be close to this because we're trying to do a good job of predicting the price of the house or something. Right? On the other hand, well, geometrically, you might say, well, like, why not do the horizontal distances? Looks the same. Well, no, because it doesn't correspond to this, which is actually saying do something useful, predict the correct output on xi. Right? So that's kind of part of the reason that people look at this, is that this actually corresponds to the original task of actually predicting rather than just drawing a line through the points, which is not the same task. However, intuitively, you can kind of think of, like, usually there wouldn't be much of a difference. Like, you could even draw the ellipse thing in case, so this you would take, I think, in second semester, first year, if you're in first year. So in order to figure out the angle here of the ellipse, what you would need to do is you would need to compute the covariance matrix of the coordinates here and then take the first eigenvector of that. So that's coming up. So, okay. So this was kind of a distraction. Basically, what we're doing, trying to find the best line through the data. Now, a lot of the time, you don't just have one input feature. You don't just have one input. So, for example, you might have the square footage, but you might also have whatever the number of bathrooms, or like the square footage of the yard, or something like that. Right? So in that kind of situation, it's kind of the same. It's just that the geometry looks more complicated, right? So here, you're still trying to predict yi, so the price, for example, for the ith house. And then you have an x1 and also an x2 and also an xn. So here you have n what's called input features. And you're trying to find the best a's such that this part predicts y as well as possible. So geometrically, it looks like this, right? So rather than having just a two-dimensional scatter plot and just having a line through it, it's that you have, well, in this case, like, it's harder to draw if you have more than two inputs, but if you have two inputs, it would look like you have a 3D space where you have the points. So for example, x1 would be like the square footage, and x2 would be the square footage of the yard. And then you have the points, so the actual y's. So for this point, for example, kind of you have whatever x1 over here, and, well, the x1, sorry, is over here, and then whatever x2 over here, and then the price is this much. And then kind of the equation a0 plus a1 x1 plus a2 x2 and so on, that corresponds to a plane in 3D space. So if you have a new house where the x1 is this much, sorry, this is x2. So where the x2 is this much and the x1 is this much, then in order to predict, what you would do is you would start here and you would predict somewhere over here. Make sense? So that's the basic idea. So a lot of the time, and actually kind of right away, you'll see that just applying this idea doesn't work that well, in part because the relationship between the inputs and the outputs is not always a straight line. So here's an example. So in Gapminder, you can try to say, I'm going to figure out the relationship between the GDP per capita and the life expectancy. And if you plot all the different countries in all the different years for like life expectancy versus GDP per capita, what you'll see is something like this. And if you try to draw the best line through that data, what you'll get is something like what's on the left, right? So it's not doing a great job of predicting much of anything, and that's because the data is not really linear here. Now, on the other hand, if you take the log GDP per capita, so here what's been done is you see that kind of the GDP per capita here is 10 to the 3, and then here it's 10 to the 4, and here it's 10 to the 5. So basically I just transformed the axis in such a way that the growth here is logarithmic. sorry, to go over that exponential, what you'll see is that suddenly you do have this line that you can draw through the data easily. Right? So how do you think about this kind of algebraically? Well, so here is just a graph, so I just kind of compressed the axis by a lot, right? So here it's like, instead of kind of a constant increment of 10,000, here it's like you go this much and it's times 10, and you go this much and it's times 10 again. So that's the same as just saying log of life expectancy is equal to 3, log of life expectancy is equal to 4, log of life expectancy is equal to 5. So we'll see some examples in the code. So doing that allows you to predict much better, right? Because if you just predict by just trying to draw this line, it's not going to work. On the other hand, if you say life expectancy is log of GDP per capita times A1 plus A0, then you can predict pretty well. So, okay. So I want to show you how this is done in R. So that's like that. So I'll load this. So this is Gapminder. So let's say that I want to predict the life expectancy again from the GDP per capita. So I can do that by saying lifex tilde GDP per cap. And I have to specify that the data is Gapminder. So if I run this, I'll get my equation for predicting the life expectancy from the GDP per capita by minimizing the sum of squared errors. So this is saying, so I'll copy this. So this is saying the intercept is this much and the coefficient is this much. So this means that is approximately this much, so the intercept plus this much. So this is the equation for the line here. Okay. So I can now ask, well, how well am I doing here really in terms of predicting? So in order to do that, I need to actually get the predictions. So I'll store this in model 1, so I can do it like this. So model 1 I can still display this way. And then I could do it manually, right? So I could make the predictions, or I can use the predict function. Like this. And what I'll get is the predictions for every line in Gapminder using model 1, so using this formula. So I can say that this is my predictions. And then I can compute whatever measure of how well I'm doing that I want. So I can, for example, so in the first place, I'll just plot the thing. So you can plot y versus x like this. So I'll say Gapminder life expectancy and preds 1. Doesn't want to do that. So I just need to do this. And this is what it looks like. So in general, we see that we're doing something useful, right? So it seems that if the life expectancy is larger, the prediction is larger as well. But ideally, it would be a straight line, right? So ideally, it would be the case that the life expectancy is 30, so I predict 30. The life expectancy is 40, I predict 40. The life expectancy is 50, I predict 50. So ideally, it would be a straight line if I was doing a really good job of predicting. It would be really bad if it was just a horizontal line where the prediction doesn't have anything to do with the life expectancy. So I'll do the other thing that I suggested, which is to use the log of the GDP per capita in order to predict the life expectancy. So I'll name it Model 2. And I can say what Model 2 is. So Model 2 is the life expectancy is -9 plus this much times log GDP per capita. And then again, I need to do, I'll predict. So I'll just say preds 2 and I'll say predict Model 2. So here, this is the model. So the model is the set of coefficients. And then I'll say I'm predicting on Gapminder. So here, note that this should be new data. Unfortunately, if you say data but not new data, it's going to work. It's just not going to do what you expect it to. So always just say new data when you're using predict. And here, I'll again plot those. So now I'll plot preds 2. And you see that this is much more like a straight line. So that's good. Because ideally, you would just have a thin straight line where, like if the prediction is 40, the actual answer is 40, the prediction is 50, the actual answer is 50, and so on. So ideally, this is a completely straight line. This is much more of a straight line than what we had before. So we can also just compute how well we're doing in terms of what we're trying to accomplish, which is the sum of the square differences between the actual answer and the predicted answer. So how can we do it? Well, I can say Gapminder life expectancy minus preds 1. So this is all the differences for all the entries. I can now square all of them, and I can now sum them up. So that's going to be this much. Now, it looks like a large number, but note that this is squares, and the larger your data set, the larger the sum of squared errors. So if I do the same thing with preds 2, what you'll see is that the sum of squared errors is much smaller. So you do a better job of predicting if you say, I'm going to predict using the log rather than using the origin. And that's not always going to be the case, but you want to try different things. All right, let's see what people are saying on Discord. All right. How is the model derived? Is it by combining all the countries' data together? Yeah, so we are we are doing all the countries together. You could, in principle, just filter for a particular country and try to model for one particular country, but there's probably not enough data for any particular country, sorry. So you want to combine the data in some way. Now, there's advanced techniques for kind of saying a little bit it should be specific to each country, but then it should also be. But then it should also use the entire data set for everything. So one thing you can do that's kind of intermediate is to use the continent in order to adjust your prediction. And in fact, that's going to make it better. So if you say something like model 3 is LM, and then you say you're still predicting life expectancy, but you're using this, and you're also using the continent. Yeah, they spell it like this. RL effects. So data is gapminder. So if I now compute again the predictions, and now I'll sum all of those up, what you'll see is like modestly better, right? So we went down from 98,000 sum of squared errors to 84,000. So of course here, if I add the country as well, that would do even better. It's more of a question of, if I do that, is it going to just work on my training set but not generalize to the future, which it probably wouldn't, but that's something we discuss later on. But using the continent I think makes sense. And then also using something, so this is really advanced stuff, but if you want to look partial pooling, you can do something intermediate between just doing a separate thing for every country or doing a model that just doesn't look at what the country is. So, all right. Yeah. All right. So this is that. So now I already used the continent. So the continent is what's known as a categorical variable. So a categorical variable is a variable that's not a number, right? So if the variable is a number, you can do like a0 plus a1 times x or something like that. Even something that's discrete, so for example counts, like if you count, okay, like how many classes did someone get an A plus in, that's not really a continuous quantity, but you can still treat it as a number. On the other hand, something like country or like continent is not something that you can plug into a0 plus a1 times x, right? So some things can be considered kind of either categorical or continuous. If you think about color, for example, you might argue, okay, like what's a color? Well, that's like the frequency on the electromagnetic spectrum, right? So a frequency is a number. But people don't really perceive colors that way. And kind of the eye is not really built exactly that way, and just detecting the frequency. So color, for example, is like maybe not necessarily continuous, or at the very least not one-dimensional. Something like a Likert scale response. So that's referring to like if you have a survey, and on the survey it's like strongly disagree, slightly disagree, neutral, agree, strongly agree. So this is like a 1 to 5 scale. And that's obviously not continuous, so you don't get to say like 1.355 or something. But treating it as continuous anyway might be a little bit fraught, because it might be that kind of neutral is not the same kind of thing as strongly disagree, and not the same kind of thing as strongly agree, so you can't just treat it as a number that's between them. So that's going to be kind of specific to the data set. So anyway, how do you deal with those mathematically? Well, the trick that people use is what's called indicator variables. So for example, if you have a continent and you want to predict different things for different continents, what you would say is, I'll introduce those categorical variables. So capital I usually is how it's used. So like I1, I2, and so on. And then I1 would be 1 if for data point I, it's continent number 1. And otherwise it would be 0. And then I2 would be 1 if it's continent number 2 for row number I, and it would be 0 otherwise. Right? And that way, so if you have, for example, 5 continents, and technically people, for like k continents, people would do k minus 1, but that's kind of a technicality. So basically, it's like if it's continent 1, then this one is turned on. And if it's continent 2, then this one is turned on. If it's continent k, k minus 1, it's this one that's turned on. And then the equation would look like this. So you're predicting y, and it's going to be this term plus this term plus this term plus this term plus this term. And then only one of them is only ever going to be non-zero, because it's either continent 1 or continent 2 or continent 3 and so on. Now, the small technicality there is you need k minus 1 of those indicators if you have k continents. And that's because what you want to do is you want to be able to predict 5 different things if you have 5 different continents. And the 5 different things that you could predict is either this, which would be none of the i's are on, or it could be this plus this, and this would be if this is 1, or it could be this plus this, and that's if this is 1, and so on. Right? So with just k minus 1 i's, you get to predict k different things, and that's because you can just predict A10 by itself. So, okay. So we've already done the example with the continent, but we can now look at it in more detail. So if I look at what model 3 is, what you see is that the coefficient is like this, right? So here, what's the equation? The equation is always this much plus 6.4 times log GDP per capita, plus 7 if the continent is Americas, plus 5.9 if the continent is Asia, plus this much if the continent is Europe, plus this much if the continent is Oceania. And then Africa is left out, you'll notice, and that's because for Africa, the prediction would just be the intercept plus 6.4 times log GDP per capita. Does that make sense? Questions? Okay. Switch to Discord. All right. So that's like that. So we'll do another example. This is the Titanic data set. So that's like, so people use it a lot, like maybe kind of more than they should. But anyway, so the Titanic, so kind of the RMS Titanic was a passenger liner, a big ship. As you probably know, there was a movie about it, collided with an iceberg during actually her maiden voyage. And unfortunately, just about 700 people survived. So from kind of a data science point of view, it's kind of interesting because there is data about all the passengers because they bought tickets. So it was all written down. And you can get the data. So if you do install packages Titanic, you can then look at Titanic train, and you'll have all the data. So you have the survived column, which is 0 if they didn't survive, and 1 if they did. You have P class, so that's the class. So there were 3 different classes for passengers. So like first class is the best, most expensive, and then third class is the worst and least expensive. You have the name. You have the number of siblings that the person had. Not sure what this is. You have the fare that they paid, stuff like that. So the reason this is interesting, kind of again from a data science point of view, is you can do analysis about like, can you predict whether the person would survive if all you know about them is, you know, what class they were, what percentage, and so on. So one question that people asked about it was, so it's been said that the policy that was followed is kind of like women and children get saved first, and you can check, like, is it true? And on the Titanic, it turns out to have been apparently true. People then did studies on kind of other ships that sunk, and that wasn't the general policy, or at least like wasn't the general outcome. But on the Titanic, it is true. So similarly, you can look, and like, so it's not kind of a big secret. Like, it's known that people in first class got priority for kind of the rafts or whatever. But you can see that in the data as well. So what we're going to try to do is we're going to try to predict whether the person survived or not based on whatever data is there. So we're trying to predict categorical variables, so died or survived. So drawing a line through the data doesn't make as much sense because the only possible outputs are 0 and 1. So it's not like you have like a data through which you can expect to draw a line. So what we're going to do is something that's kind of like what we've done before. So we're going to be predicting, again, an outcome. But the way we're going to do it is we're going to estimate the probability of survival. And the way we're going to estimate the probability of survival is we're going to try to do as good a job as possible of having this formula, and I'll clarify what the formula means, but like try to find the best A's such that you predict as well as possible. And what we mean by predict is you compute this, you then transform it using the sigma function. So the sigma function is the logistic function, which looks like this and has this formula. And then we'll try to do as good a job as possible of trying to make the P be close to 1 if the passenger survived, and close to 0 if the passenger did not survive. So the reason we kind of do this slightly complicated thing is that we can't really draw a line through the data because, again, the y's initially are just 1 and 0. So what we're trying to do is we're saying, okay, like, we'll compute the probability, which is between 0 and 1, and which is going to use the same kind of formula. And then we'll make sure that the probability is between 0 and 1 because probabilities need to be between 0 and 1. The way we accomplish it is by just computing an arbitrary number and then plugging it into the logistic function. The logistic function basically is always between 0 and 1. Not basically, it's always between 0 and 1. And then it basically squashes whatever input is to that range. And then 0 goes to just 0.5, and then if it gets to be like larger than 6, then it's pretty much 1. If it's smaller than -6, it gets to be pretty much 0. Make sense? So when predicting what we're going to do, so once we found kind of the best possible A0, A1, A2, and so on, we're going to say, I want the probability to be as close as possible to 0 when the person didn't survive, as close as possible to 1 when the person did survive. And we can kind of sort of interpret this number as the really kind of the probability if we didn't know and if we had to bet would this person survive or not, like this is our estimate for whether they survived or not. This is not an exact science kind of thing. It's not really a probability. It's just an estimate that's between 0 and 1 that kind of corresponds to more likely to survive, less likely to survive. It's only a probability under a very restricted set of assumptions which are not usually satisfied. So in practice, the way we do it is very similar to what you would usually do. So you would just say, so this is Titanic train. So you would say GLM instead of LM. And here, maybe you want to use the sex and the age and the class. So for the purposes of this class, I'm always going to say family binomial. I'm not really going to go into the details. I can post readings about this if you like, but we're basically always saying family binomial. So we run this like so. And you can look at model Titanic. And what this is saying is that the probability of survival is, so that's the sigma of 5.05 minus 2.5 times, so I'll name this I male. So this would be 1 if the passenger is male and 0 if they're not. So you subtract 2.5 if they're male. If they're not, you don't. And then we say minus 0.037 times age. And you say minus 1.28 times B class. So here you can look, and I'll again remind you, so sigma Z is 1 over 1 plus x minus z. All right. So here you can kind of see the story in the coefficients that I was talking about before, right? So this is saying if I male is 1, then you subtract 2.5. So you make the input to sigma smaller, so you make the probability of survival smaller. If your age is larger, then you subtract more here. So again, like the larger the age, the smaller the probability of survival. Here you see minus 1.28 times B class. So this is saying, so class, if you remember, is like first is best and then third is worst. So if you're in third class, your probability, which is the cheapest one and kind of the lowest social class, generally speaking. So the higher your class, meaning like if it's like third class, your probability of survival is smaller because you're subtracting here. All right. So that's like that. This is just kind of the coefficients, right? We could also just ask, okay, well, how well are we doing at predicting here, right? So what you can do, so we have our model Titanic, so you can say predict. And so for now, I'll just use Titanic train. So this is going to be the A0 plus A1x1 plus A2x2 and so on. So I can transform it by using, so plogis is the built-in R function that computes sigma. So that's just this. And that's going to give you the probability for each of the passengers, whether they survived or not, according to the model. I wonder why for 561 it's not predicting anything. Oh, it's actually for, yeah, so 561 as well. So that seems fine. Yeah, so this person didn't have an age. So for that reason, you can't really make a prediction here, which is unfortunate. So that's okay. So we have those probabilities, but now how do we summarize, like, how well are we doing in terms of predicting? Well, what you can ask about every one of those probabilities is it larger than 1, or is it 0.5, or is it smaller than 0.5? So I can say greater than 0.5. And now I have a bunch of trues and falses. And then true kind of suggests better than 50% probability of survival. False suggests not better than 50% probability of survival. And now I can say, okay, so how does that correspond to whether they actually survived or not? So I can just ask, like, is it equal to survived or is it not equal to survived? So here true means it was either greater than 0.5 and they actually survived, or it was smaller than 0.5 and they did not survive. Then it's true. If there's a mismatch, then it's false. So now I can just figure out how many of my guesses were correct. So how many trues there are there. So I can just say I want the mean of that. So trues get converted to 1, falses get converted to 0. So the mean is just the proportion of the trues. So here it's going to be just an A, and that's because there were some predictions which were neither, because the age was not recorded. So I can say an ARM is true, and that would get rid of the NAs and just get me the percentage of the cases where I had a true, where it was either true or false. So here it says 79 of the guesses by the model were correct. Is it good? The answer is we don't know. And the reason is whether it's good or not depends on how difficult the task was, right? So if I have a coin that always lands heads, because it's actually very difficult to make a coin like that, but so you can load dice, that's easy. You just weight kind of the side of the die that you want. With coins, it's actually, people tried it, it's actually like very difficult to make an unfair coin. But let's say that you had an unfair coin, and if it landed heads 95% of the time, then it wouldn't be very impressive if you guessed correctly whether the coin landed on heads 95% of the time, because you can just guess the same thing every time. Similarly, is 79% impressive? Well, it depends on what you could do by just doing the dumbest possible thing and saying, well, did more people survive or die? I'll just predict whatever is the majority. And we can figure out what the majority is, right? So we can say, so what's the mean? So what's the mean for this? So this would be, not model, sorry. So Titanic train survived. So 38% of the people survived. So that means that if I want to guess correctly, what I want to do is just guess did not survive every time. And if I did that, then I would get it 61% correct, well, 62% correct. So that means that getting it 79% correct is better than the dumbest possible thing I could do, which is just guess the majority every time. Well, not the dumbest, but like the easiest thing that still kind of makes sense. So that's like a common mistake that people make of like not doing that, and not. So this is sometimes called the base rate, not looking at the base rates, because kind of without that context, whether 79% correct is good or not, you just don't know. It might be very bad. So this is this. So I'll leave you with kind of the last thing, which is that here what I was doing is I was basically finding the best coefficients here such that the probability on the training data, on the data that I already have, is as good as possible. So one thing I could do in order to get perfect prediction. So actually, does anyone have an idea for how can I get 100% prediction, correct prediction with my data here? So to remind you, this is the data. So, yeah.
You could write like an equation that gets everything in mind. Like
Yeah. Exactly. And actually, I don't even need everything, right? I just need their name. So if the name is in the equation, then it's going to be great because I'm just going to write down what happened to everyone, and that's the end of it, right? Of course, the problem with that is that it wouldn't generalize. So it would do very well on whatever data I use in order to find the coefficients, but the names won't even repeat in new data. So what we'll see next time is what's called the train validation test split, where what you do is you set aside a training set, which is you pretend that, well, not pretend, you know the answer is there, and then you set aside a test set which you pretend is like the new data, so you don't touch the test set, and you don't use it in order to get the best coefficients, and then you can use the test set in order to evaluate how well you do on new data, because the test set is like new data, you're not using it in order to set the coefficients. So sometimes it's like completely silly where you just write down the name, and well, of course that's going to work well in the training set. It's not going to work at all in the test set because in the test set you'll have new names. Sometimes it's a bit of an intermediate situation where, like you suggested, you just kind of write things that do make sense, right? But you write everything down, but then you adjust the coefficients in such a way that it works really well in the training set, but it might not work well in new data. So yeah, what's happening on Discord? So you just need to install packages Titanic, and then when you do library Titanic train, then you'll see it. So plogis is just this, like it's just this function. And that's for logistic function. It has like a weird backstory for why it was named that. Look it up on Wikipedia, it's fine. So this is just because if we don't have it, then sometimes NA just means not available, and that would be not available because the age of the person is not available, so you can't make a prediction. And then R, by default, if you just tell it to compute like whatever the mean of this, it'll say, I don't know, because you have an NA there. If you say, I want to ignore the NAs, you can do that with NA.rm. So yeah. How different is RStudio from Python? Well, I mean, really RStudio is like a specific environment for using R, so the real question is how different are R and Python. And And the difference, so like it's actually kind of a difficult question because you can write in Python and it's almost like R, and you can write in R and it's almost like Python, but the kind of cultures around Python and R are different. So even though you can make R very similar to Python and you can make Python very similar to R, that's not how people usually write in them. And part of it is in R, the thing that's really different in R is that you can write those kinds of formulas. In Python, you can of course do that, it's just annoying. So R is usually used for data analysis, and it's used kind of in the style that I'm teaching. You'll see when you learn Python is that at least the way most people write Python is quite different from what we're doing here. And part of it is just they're suited for different problems. So if you're specifically working with data frames, R is arguably better. If you're doing anything else, then Python is arguably better. In part, it's like Python is just outright faster. Part of it is in R, like specifically writing this kind of formula is like a much nicer experience in R than in Python. But really, it's a small difference. Mostly, it's about just different problems being addressed and different cultures about how you address the problems. All right, I'm done. So I'll fix the problem set and post it in like about half an hour. And I suggest that you do it by kind of Monday or Tuesday or something like that. We're not doing. I guess I'll do the in-person lecture one more time on Tuesday, and then I'm leaving. Kind of starting next Thursday, it's going to be online only. Next Thursday is canceled. So starting the Tuesday, because like that's my flight, is actually on Thursday. Next Tuesday we're going to be back, but online. And not at the same time, we'll reschedule. Survived predicted from survive is kind of weird, yeah. There's no autograder for problem set 1, right? Because you actually submitted, and it wasn't like a while back. It was like a week ago. Give me time. I'll check it, and But basically, kind of the feedback that you get for problem set 1 is just what ChatGPT said. So I'll just check that you actually didn't submit like something that doesn't make sense, but otherwise, if you submitted it, then you're good. All right. Other things? The linear regression PDF is on the website. It is. It isn't on the website. I thought I posted it. Yeah, it's here. All right. Yes. So the problem set 3. I don't know. I haven't really decided. Like maybe, or maybe you just go. I think there will be a problem set 3 actually, and then there will be a project. Yeah. All right. Okay. Thanks very much. See ya. Bye.